Hi, hello everyone. Today my topic is about most interesting thing in electrical engineering, which is nothing but harmonics. Actually, I would like to explain about harmonics. It means what are harmonics, how do they how they are produced, how they entered into the system, and after entering into the system, what effect they cause, and finally, how can we mitigate and how can we reduce the harmonics? So today we will go discuss about total topic about harmonics. It means how they are produced and what effect they cause and how can we mitigate harmonics. I mean, what process do we use to mitigate harmonics? So before going to say about that, I would like to introduce, like I would give glimpse about harmonics. What are harmonics? Harmonics are nothing but they are unwanted frequencies. For example, if you have a ceiling fan, if you give some voltage like V is equal to Vm sin omega t or I is equal to Im sin omega t, where omega is fundamental. If you give this voltage to ceiling fan, the motor present in the ceiling fan experiences smooth operation. Whereas if you connect a ceiling fan to the inverter, for example, if you have lost in power supply, if you give ceiling fan supply with the inverter, then the inverter output is nothing but it's a square wave output. And if we give square wave output to ceiling fan, what happens is there won't be a smooth operation in the motor of ceiling fan. There will be wear and tear. Why? What happens? It's nothing but, see, according to Fourier said that any periodic signal can be converted into the multiple frequencies of sinusoids. For example, what I'm going to say is, if we give square wave input to the ceiling fan will have the wear and tear in the motor, and it will rotate in abnormously some different by making noise. It will rotate by making noise. On the other hand, if we give pure sinusoid to the ceiling fan, it will operate with smooth operation. It means motor present ceiling fan will operate with smooth operation. What happens when we give with a square wave pulse means, square wave pulse is nothing but, since it is a periodic waveform, square wave we can define square wave as a sinusoid only but with multiple frequencies. Since square wave has positive pulse and negative pulse in one cycle, it's nothing but it exhibits half wave symmetry. We can express square wave as the addition, as the algebraic sum of sinusoids. For example, a pure sinusoid nothing but V is equal to Vm sin omega t, but a square wave is nothing but V is equal to Vm1 sin omega 1t plus Vm3 sin omega 3t plus Vm5 sin omega 5t. In this way, there are harmonic frequencies present in the supply. Here, if we have only fundamental frequency, we have smooth and smooth and well operation of the motor. But if the extra frequencies come, when the problems comes in the system when the extra frequency is added. So today we will going to learn about that. So how they are produced, how they are produced from source side, from load side, how they are produced, and what are the effect of harmonic, and how can we mitigate the harmonic present in the system. For example, I am taking an ideal sinusoid where there are no harmonic frequency. For example, V is equal to Vm sin omega t, for which produced current is I is equal to Im sin omega t. So this is nothing but this is an ideal sinusoid. If we give this voltage and current to the ceiling fan, what happens is, this is nothing but ideal sinusoid. If I give this voltage signal to the ceiling fan, then there will be a smooth operation. Anything, if you give this to the table fan or else ceiling fan or any electrical appliances, there will be a smooth operation of the motor present in the machine. Why? Because there are no unwanted frequencies present in the sinusoid. But In real nature, what happens is, due to the due to the due to the application of non-linear elements in the electrical system. For example, you see here I have explained about ideal sinusoid. So when there are not when we use non-linear elements in the system, like for example, if we use IGBT or IGBT switching element or transistors or GTOs, or else if we, for example, if we operate transformers in saturation region, if we operate alternators in saturation region, if we operate transformers, saturations, and inductive cores, if we operate in saturated regions, they will produce the harmonics in the system. It means, what I'm going to say is, when we use non-linear loads, or else when we use switching elements, or else during transients. Transient is nothing but we changes sudden changes in time. For example, if there is a switching action taken system, there is a chance of producing harmonics in the system. Actually, I have explained how the harmonics are produced in the system. I repeat, harmonics are produced in the system due to due to by the with due to the usage of non-linear elements in the system. Like, non-linear elements are nothing but IGBT switching element, and for example, transformer. If you use transformer in saturation mode, if you use alternator in saturation mode, if you use inductive course in saturation mode, if we see, until unless we use electrical machine in region, if we operate electrical machine in linear region, there are no harmonics what is on the system. Harmonics are produced only when we operate electrical machine in non-linear region. When and only we apply in non-linear region, and when we use non-linear devices like IGBT, transistor, GTO, and MOSFET, when you use these non-linear switching element in the system, they do causes the harmonics in the system. And now I have explained about how do the harmonic causes due to switching elements, and we are when we operate electrical machine in non-linear mode. Now I am going to explain after the production of harmonics, and what are the what effects do we get. For example, what losses we do get. Does the efficiency decreases, or else how can we eliminate harmonic frequencies. Now I will explain a while. So here, what I'm going to say is, when there are no harmonics, V is equal to Vm sin omega t is the waveform. But when when the harmonics entered into system, what happens is, and see, this is V is equal to Vm sin omega t is nothing but ideal sinusoid, for which current producing is Im sin omega t is nothing but current produced. So when harmonics created in the system, for example, due to the non-linear application of load, or is if the electrical machine applied, if for example electrical machine is operated in non-linear region, there may be a chance of production of harmonics. After the production of harmonics, how can we represent it in mathematical form is, V is equal to Vm1 sin omega 1t plus Vm2 sin omega 2t plus Vm3 sin omega 3t plus, in this way continuously, omega 1, omega 2, omega 3, omega 4, in this way continuous multiple frequencies are produced in the signal. In the similar way, if when we apply voltage, similarly current is also produced in the same way, depending upon the load. For example, resistance is nothing but in phase, inductor means nothing but with a lag of 90 degrees, pure inductor. If there is a pure capacitive load, then the current will come with a leading of 90 degrees phase lead. So in this way, depending upon load, current will come. Current will come in such a way that Im sin omega 1t plus Im2 sin omega 2t plus Im3 sin omega 3t. In this way, multiple frequencies are getting. So what happens? Why? See, these are multiple frequency. In order to operate, in order to operate our load with a smooth and with smooth operation, in order to operate our motors or with a smooth operation, we only need this fundamental is nothing but this omega 1. Omega 1 is nothing but this is the only required frequency for us for the smooth operation of an electrical machine. But there are the other frequencies which are not required for us, this omega 2, omega 3, omega 5. These are unwanted frequency. We don't require that frequencies. That frequencies are responsible for the losses present in the system. That frequencies are responsible for the reduction of the efficiency of a machine, and that systems are responsible for the heavy losses like copper losses, hysteresis losses, and eddy current losses. So final our agenda is nothing but we need to remove these unwanted frequencies. How can we remove this unwanted frequency? I'll explain in a while. Finally, what I'm going to explain is, for example, ideal sinusoid is nothing but this is the ideal sinusoid, which is nothing but v is equal to vm sine omega t. Omega is nothing but 2 pi fu. So this is the fundamental frequency. In India we follow britishers frequency, like for example, that is nothing but f is nothing but 50 hertz. We took from England. So 50 hertz nothing but, see, in 1 second, it will make 20 millisecond. It means 20 means, so for example, this is one cycle, which is nothing but fundamental frequency. If I want to if I want to if I want to draw if I want to draw to for example, if I want to draw, see, I will explain here. See, I am drawing one nothing but, this is nothing but fundamental. For example, if I want to draw sine 2 omega t, this is nothing but this curve is nothing but v is equal to vm1 vm1 sine omega 1 t. Now I am going to draw sine 2 omega t. Sine 2 omega t is nothing but, in one cycle itself, it means in one cycle of fundamental signal, there will be two cycles of for example, this is nothing but v is equal to vm to sine 2 omega t. In the similar way, if I want to draw 3 omega t, for example, if I want to draw vm3 sine 3 omega t, 3 omega t is nothing but, in this fundamental, what I have said, this fundamental one cycle is producing three cycles of, for example, in one cycle only we will produce totally by this time only, totally there are in one cycle of fundamental supply, there are three cycles produced, 1 2 3. By this end cycle will be ending. It means what I'm going to see, for one cycle of fundamental voltage, one cycle of fundamental signal, if for example, if you want to draw 2 omega t by sine 2 omega t, there will be two cycles present in the one cycle. It means, for example, in one voltage signal in 20 milliseconds, there will be one signal. In the similar way, to sine 2 omega t means in 20 milliseconds, two signals will be having. For example, Vm sine 3 omega t, it means in 20 milliseconds, there will be three voltage signals, is three sinusoids. In these are three sinusoids. For example, if there is for example, there are 10 sine 10 omega t, for example, 10 omega t with respect to fundamental. For example, this is nothing but fundamental. With respect to fundamental, there will be, for example, sine 10 omega t means in one cycle. Here, in one cycle, there will be 10 sine signals in the small. For example, if I take 24 sine omega t, in 24 sine omega t, what happens is, in this way, small signals, in this way, small signals, in one cycle of fundamental signals, there will be 24 cycles of signal, 24 cycles of voltage signals. What I'm going to say is, the order of frequency, fundamental is nothing but, for example, what I'm saying is, fundamentally, for example, if there is for example, I can derive it as fn is equal to n into f. For example, if I require fundamental, if you keep f1 n is equal to 1, this is nothing but order frequency 1 into f. If you require third frequency, f3 is equal to 3 into f. if we in the similar way, if we equal nth frequency n into f. And one more point we have observed in this signal, what happened is, if I go on increase my frequency, for example, what I have said this is nothing but fundamental for two omega t. What I have said, in this one cycle only two signals I have driven. Okay, in this two signal, in the similar way, for 24th for 24th frequency, what I have done is, in the similar, okay, in this small signals have totally drawn 24 cycles of signal in only one cycle of fundamental frequency. If you draw in this way, what happens is, the frequency component has increased, but another point is nothing but the amplitude of fundamental is nothing but a, amplitude of this 2 sin omega is nothing but a by 2. Similarly, the amplitude of the 24th frequency signal is nothing but a by 24. It means, by which I have drawn one conclusion, that if I increase the frequency, what happens is, the amplitude of the signal is decreasing. So this is the technique we use in electrical engineering. What we basically use is, I will explain in the mitigation of harmonics. There we use basically, we'll use RLC filters, which is nothing but resistor, inductor, and capacitor. Those filters are nothing but in order to reduce the high voltage frequencies only. So finally, we use power electronics in order to reduce the low harmonics, and we will be keeping the high harmonics in the same way. And high harmonics can be removed by normal filter. We can remove high harmonics. In this way, we can reduce the filter. In this way, we can reduce the harmonics, and we can give it to the system. So finally, what I've explained is, what are harmonics? Harmonics are nothing but unwanted frequencies. Unwanted frequencies, for example, V is equal to Vm1 sine omega 1 t is nothing but this is the fundamental frequency which we require for the smooth operation of the electrical motors and all the machines. But due to the non-linear operation of machines, due to the non-linear operation machine, and due to the switching elements like IGBT, MOSFET, transistors in the electrical system, there will be causing an harmonics, for example, harmonics in the system. So due to the presence of harmonics, what happens is, I explained V is equal to Vm sine omega 1t plus Vm2 sine omega, I mean 2 omega t plus Vm3 sine 3 omega t. In the similar way, I have given voltage. The current produced nothing but Im1 sine omega 1t, I mean 1 omega t plus Im2 sine 2 omega t plus Im3 sine 3 omega t. In this way, the frequency components are increasing. This is nothing but first equation. This is nothing but second equation. So now I am going to explain what happens. What happens if harmonics are there in the system? So here with this equation only I'll explain. See here, see here, check here, second equation, I is equal to Im1 sin omega 1 t, Im2 sin 2 omega t, Im3 sin 3 omega t. In this way, my current component is increasing. My fundamental current is nothing but I is equal to Im1 sin omega 1 t. This is the only required current for me. But due to the harmonics, my extra frequencies are getting into the system, like Im2 sin 2 omega t, Im3 sin 3 omega t, Im4 sin 4 omega t, Im5 sin 5 omega t. See, by which what happens is, my RMS current, is nothing but under root of Im1 square plus Im2 square plus Im3 square plus Im4 square. In this way, my RMS current is increasing. RMS current is nothing but root mean square. Root means square current. Root means square current method is C. So you compared. If you, for example, if you give DC voltage to for example circuit, if it has given, for example, at certain point of time it has given some heating effect. In the similarly, if you give AC current to that, it will produce the same heating effect at certain current. That current is nothing but RMS current, which we can given, for example, if DC current is nothing for a sinusoid, for example, if DC current is nothing but IDC, so for the AC it will become, for instance, Im by root 2. It means at Im by root 2 point, the heating effect will be same. That is nothing but IRMS, root means square current. So by the increasing of root mean square current, what happens is, see, copper losses. For example, we use transformers, electrical motors, generators. In all, we use conductors. Conductors nothing but it is made up of copper wire. See, what happens is I is equal to copper loss. Copper loss is nothing but, for example, P loss. P loss. Copper loss is given by IRMS square into R. Here when the increasing of IRMS is there, definitely there will be a copper loss, which is nothing but which is given by IRMS square into R. It means copper loss also increases because IRMS is increasing, therefore copper loss will increases. Similarly, what happens if the increase of frequency? Here fundamental frequency is nothing but the required frequency is nothing but this omega 1 t, but we are getting extra frequencies like 2 omega t, 3 omega t, 4 omega t. What happens if the frequency component increases? For example, let us consider transformer basic. What happens is, when we operate transformer in linear region, there will be no problem, within no problem. But the problems comes, for example, until unless we apply region, no problems comes. But when you operate in non-linear region, for example, this is nothing but linear region, and at this point, it enters into non-linear region. For example, when we operate transformer in non-linear region, there may be a chances of producing harmonics in the system. After producing harmonic system, for example, for transformer, if I assume V by F as constant, what happens is hysteresis losses is given by some constant into frequency, and eddy current losses are given by some constant into frequency square. See, what I'm going to conclude is, if frequency components increases in the system, in transform for a electrical machine like transformer, whose hysteresis loss and eddy current losses are proportional component of frequency, therefore hysteresis and eddy current also increases in the system. If the losses are increased in the system, what happens is heating effect will increases. Heating effect will increases. If the losses increase in the system, if we give input as for example pi, due to more losses in the system in between middle, then the output will be less, by which efficiency, which is nothing but given by p out by p in, the efficiency will also decreases. See, these all are the effect of harmonics. If the harmonics, once harmonics comes into system, what happens is IRMS square, it means the current will increase in the system. If current increases in system, copper losses will increase, because copper loss is nothing but it is IRMS square, it means square times of current, it is proportional to square times of current. Since current is increased, therefore copper losses increases, and hysteresis losses, which are nothing but hysteresis eddy current losses present in the transformer, which are nothing but they are proportional to frequency component, and if frequency increases in the system, therefore if frequency increases, what happens? Losses increases. If losses increases, output generated will be less than the input. If output generated is less, efficiency is less. See, finally what I've explained is, by this time what I've explained is, what are harmonics? Harmonics are nothing but unwanted frequencies present in the system. How do they created in the system? They are created in the system when we use as non when we use a switching element. See, the day when we use power electronic devices like IGBT, MOSFET, transistors on switching, when we use these element as switching element, therefore the power electronics, therefore harmonics come to system. And for example, when we use alternators, transformers, inductive cores, VFD is nothing but variable frequency drive. A variable frequency drive. Today we mostly use VFD in everywhere. Even in locomotive also we use VFD drives. Where, for example, we have available supply is nothing but AC. We do basically convert into DC with the help of rectifier. Even in rectifier also we use diodes. Diode is nothing but non-linear element. It's non-linear element. When the power electronic device comes into the picture, therefore non-linearity comes into the picture. When non-linearity comes into the picture, harmonics comes into this picture. Finally, most important equipment we use VFD. When there is a VFD in system, there will be harmonics in system. See, for the in locomotive, what I have said, available voltage is AC. For converting into DC, we basically use rectifier circuit. After converting into this DC, Again we basically use filters like choke coils, and afterwards we use inverter. This total setup is called VFD drive. Inverters also, for inverters we give supply. For there also we will use IGBT for gating pulse. For switching element we use IGBT. So where are the power electronics? See, the day when we use the power electronic switches, when power electronic switches comes into the picture, there will be a situation called like a harmonics in the picture. Due to, finally I can conclude that due to the non use, due to the application of switching element and non-linear devices, and our electrical machine, if you operate in non-linear zone, there may be a chances of producing the harmonics in future. Now, how can we reduce the harmonics? I have said harmonics are danger. Harmonics, nothing but they increase the losses, they decreases the output efficiency. So definitely we need to know the mitigation step to, in order to reduce the film. So in order to mitigate, I will explain one of the mitigation step we basically use. what i have said is for example, frequency fn is equal to n into f. Similarly, an is equal to a by n. It means what I'm going to say is, for example, if we increases the frequency, for example, I have said in one video, if I my fundamental frequency is beat, if I want to, for example, if I want to 24th frequency, 24th harmonic frequency, what happens is, in this way, in this one cycle of supply voltage formula, I need to draw some small signals of 24 cycles in one cycle. This is about 24 cycles totally. So when we draw 24 cycle, definitely my amplitude will decrease, because small pulses will draw small pulses with respect to fundamental. For example, if my fundamental amplitude is a and fundamental frequency is f, my 24th, for example, my 24th frequency is nothing but 24 into f, and my 24th signal amplitude is nothing but a by 24. For example, this is the a by 24. It means this small amplitude is present here. See, if small amplitude is present, we can reduce this small amplitude pulses with the normal RLC filter. We can reduce that filter, but the seriousness comes only in reducing smaller frequencies, like for example 2 omega t, 3 omega, 5 omega. These are nothing but dangerous frequencies in order to reduce. This 2 omega t is nothing but, for example, if I give inverter, if I give inverter supply to for my ceiling fan, what happens is, produced signal is nothing but square wave. So producing filament. In most of the situation in this only, if we produce square wave is nothing but, according to Fourier, square wave is nothing but, it is a combination of sinusoids. For example, this is nothing but sine 3 omega t, sine 5 omega t, sine 7 omega t. If you all club, all these voltage signals, finally we will get in this way square wave. In this way we can write. See, square wave is nothing but, it's according to Fourier. A square wave is nothing but, it is a combination of sinusoids. For example, if I mix Vm1 sin Ia is equal to Im1 sin omega 1t plus Im3 sin omega 3t plus Im5 sin omega 3t. If I mix all that signals in three-dimensional space, if I add in algebraically, final voltage, final signal I get is square wave. It means a square wave can be converted into sinusoid with respect to Fourier. So why I have explained here means, if I give square wave to the ceiling fan, there will be nothing but, there will be, I have said here sine 1 omega t, 3 omega t, 5 omega t. I have not used here 2 omega t, 4 omega t. Their harmonics are two types. Even harmonics are there, odd harmonics are there. But in signal fan system, we have learned that if a signal is odd wave, there will be no even harmonics present in the system. Because due to the half wave symmetry, even harmonics are eliminated. But the dangerous frequency which comes into the inverter supply is 3 omega t and 5 omega t and mostly 7 omega t. That's it. In this most dangerous frequency is nothing but 3 omega and 5 omega. 3 omega and 5 omega. How can we reduce 3 omega and 5 omega? See, I have giving this square wave pulse to ceiling fan. So I need to decrease the this 3 omega and 5 omega. In what way I can decrease? So I will explain here. In what way I decrease it? In order to decrease that, we will come into the power electronics. In power electronics, there are many methods in order to reduce the harmonics. I will explain for a time sake, due to time constraint. I will explain one important method, which is nothing but sinusoidal sinusoidal pulse width modulation. Sinusoidal pulse width modulation is nothing but by controlling the, see, what we basically use in sinusoidal pulse width modulation is we basically use one reference signal, which is nothing but sinusoid, and another reference this is nothing but reference signal, and another carrier signal, for example triangular. I will explain why we use this is nothing but triangular is nothing but a carrier. This is nothing but sinusoid is nothing but a reference. In this way, basic in this way, carrier frequency and reference frequency, we pass it to comparator. We'll give input to the comparator in a such a way that when my triangular signal is less than the reference signal, then the output must be produced in the pulses in this way. For example, here you see my carrier signal. Here my carrier signal is less than here, so output is generated. Here also one output is generated. In this way, small pulses are produced. Here when my carrier frequency is less than, they here produce nothing but V. In this way, small pulses are produced. What happens when you produce? This is nothing but pulse width modulation is nothing but will basically we will select the width of the pulse. With small width pulses will nothing but we will produce pulses in a such a way that totally more number of pulses will produce in a such a way that my signal will be sinusoid. For example, see here the two pulses are produced here. If I produce, for example, number of triangular pulses we have taken, your number of pulses we have produced. For example, if I produce a number of short pulses, short pulses. In this way, if I produce a short pulses by taking the reference in this way, short pulses. If I draw diagram, when my signal will be sinusoidal, it means basically in today's life we will if we use inverter of high cost, that inverter output is nothing but it is not a square wave. See, square wave inverters are nothing but low cost equipment. If you keep if you use then high quality inverters, multi level inverters, multi stage inverters, if you use high cost inverters, basically the output of the high cost inverters nothing but that's pure sinusoid. And how can we make sinusoid means with the help of one of the important method is sinusoidal pulse width modulation. Basically in sinusoidal pulse modulation what we do is basically we will take one reference voltage and one carrier signal also will take. We compare we will give logic to the system in such a way that when my reference signal is less than the carrier signal, you produce the we will say to the processor that you produce the output. In that way when pulses are produced, see how much number of pulses we produce in the same quantity will produce the AC signal. So finally what happens if you produce AC signal, what happens when you produce AC signal, indirectly harmonics are reduced. In this way we can reduce third harmonic, fifth harmonic also, depending upon the depending upon the selection of the signal. See, VRMS is produced given by, this is nothing but in powertronics will be there 2D by pi, and VRMS output equation is nothing but, for example, in total in Fourier analysis what happened, sin 4 v 4 VDC by n pi. So what I'm going to say is uh, voltage is equal to 4 VDC by n pi into sin n omega t sin nd. It means what I'm going to say is if we control the pulse width, if we control the pulse width of signal, then we can automatically control automatically we can control the what happened automatically we can control the harmonic frequency also. Here n is nothing but order, so it's sin nd, sin is nothing, n is nothing but order. Here also V RMS in a Vs is equal to 2D by n pi. It means by selecting the harmonic component, for example, if I want to reduce third harmonic, I will place 3 in place of n. If I want to reduce the fifth harmonic, I'll place 5 in case of n value. And so by giving this logic, we can reduce the, see, most danger frequency are third and fifth harmony because their amplitude is high range amplitudes are reduced by only pulse width modulation only. In due to bipolar electronics techniques only we can reduce high amplitude frequency components. Low amplitude frequency component, for example, if I want to reduce the 24th to 22nd harmonic, their amplitude is less, we can reduce the 24th harmonic component with the help of small RLC filter. But if you want to reduce the high harmonic filter, we need to use a high with high techniques, like in power electronics what we have sinusoidal pulse modulation and other the pulse width modulations are present, by which we can reduce the harmonic. So finally today I am going to give glimpse about what I have explained today. First, I have started with harmonics. Harmonics are nothing but they are unwanted frequencies. Why unwanted frequency? How do they came into the system? They came into the system due to the application of non-linear switching elements like IGBT, MOSFET, transistors, and even electrical machines which we use basically in power system like generators, motors, and transformers. When these machines operated in non-linear region, there are also chances of producing harmonics. So I explained how do the harmonic produced from source side and from load side also. And after the production of harmonics, what happens is frequency component increases means frequency increases. If frequency increases means eddy current losses, hysteresis losses, and if frequency component increases means IRMS, I mean current also increased, by which copper losses also increased. When losses are increased, definitely we have given input as PI, when there are more losses in the system, definitely output will be less than the input, by which my efficiency also decreased, my heating effect also increased. So this in this way I explained the effect of harmonics. And after the production of harmonics, how can we reduce the harmonics? I have said, as the number of cycles increases, as the harmonic range increases, as the order of harmonic increases, amplitude will be decreased. See, for higher order harmonics, like for example, 20th harmonic, 50th, 15th harmonic, 17th harmonic, 18th, 19th harmonics, their amplitude is so small. For example, if fundamental frequency amplitude is A, 17th harmonic frequency A by 17, which is less than the fundamental, that can be reduced by using small filter like RLC filter. We can reduce the higher harmonic frequency, but lower order frequencies are most dangerous frequencies, nothing but third harmonic and fifth harmonic. They are dangerous. They can be reduced by the circuit property. For example, in power electronics we basically reduce with by using some techniques like sinusoidal pulse width modulation. And in case of, for example, in case of transformers, how can we reduce third harmonic, how can we reduce it is reduced by by the connection, for example, if you give delta, there will be circulating current. If you give trans, for example, if you use star connection, if you ground the star connection, therefore the zero sequence components or else any harmonic current produced, they will go through the ground. In this way we will reduce we will reduce the harmonics. And finally our agenda is to give harmonic less voltage and harmonic less current to the load for the smooth operation of electrical motors. Thank you.